Hi everyone, I am here to present the topic about stress strain curves and its properties. The stress strain curves shows how a material deforms when a load force is applied. It helps us to understand the strength and the flexibility of materials like steel, aluminum. A stress strain curve is a graphical representation of stress on y-axis, strain on y-axis, showing how materials deforms under load, crucial for determining key mechanical properties like elasticity, ductility, stiffness, and strength. It defines behavior throughout distinct region: elastic, linear, reversible, plastic, permanent deformation, and fracture. A stress in a material is the internal resistance or intensity of force per unit area that develops when an external force load is applied. It represents the internal force distributed over a cross-sectional area. The SI unit of stress is Pascal PA, N divided by M square, Newton per square meter. And the stress is equal to force divided by area. Strain in a material is the geometric measure of deformation or change in shape or size relative to the original dimensions caused by applied stress. Strain change in length divided by original length. Strain equal to x1 minus x0 divided by x0. Del x0 divided by x0. Hooke's law states that within a material's elastic limit, stress is directly proportional to strain. It describes the linear elastic behavior where materials return to their original shape after deformation. The law applies to tensile, compressive, and shear stress provided the deformation is small. Stress is directly proportional to strain. Stress strain curves. The stress strain curve is important because it allows engineers to quickly determine several of the most critical and fundamental mechanical properties of any material. A single tensile can be produced a stress strain graph which then allow the following properties of a material to be obtained: Young's modulus, yield strength, ductility, yield point, plastic region, elastic region. There are several stages showing different behavior which suggest different mechanical properties. To clarify, metal can miss one or more stages. The linear portion of the curve is the elastic region and the slope of the region is modulus of elasticity or Young's modulus. Plastic flow initiates at the upper yield point and continues at the lower yield point. The appearance of upper yield point is associated with the pinning of dislocation in the system. In a elastic region, initial linear portion of curve material returns to the original shape follows Hooke's law, no permanent deformation in the elastic region. In a yield point where the plastic deformation begins, material will not return to original shape. Yield strength indicates safe design limit. Mild steel shows upper and lower yield point. In Young's modulus, slope of a elastic region indicates the stiffness of material. Higher, stiffer material measured in GPa. The plastic region beyond yield point, permanent deformation occurs. Stress increases with strain. Material undergoes with a strain hardening. The first stage is the linear elastic region. The stress is proportional to the strain, that is, obey the general Hooke's law, and the slope is Young's modulus. In this region, the material undergoes the only elastic deformation. The end of the stage is the initiation point of plastic deformation. The stress component of the point is defined as yield strength. The next stage is strain hardening region. This region starts as the stress goes behind the yield point, reaching a maximum at the ultimate strength point. Is the maximum stress that can be sustained and it is called ultimate tensile strength. UTS. The stress is mainly increases material elongated except for some material such as steel. There is nearly flat region at the beginning. And the third stage is necking region. Behind the tensile strength, a necking forms where a local cross-sectional area becomes significantly smaller than the average. The necking deformation heterogeneous and will reinforce itself as stress concentrates more at the reduced section. Such positive feedback lets quick development of necking and leads to fracture. Note that of the pulling force is decreasing, the work strengthening is still progressing. Toughness and ductility. Toughness is a material's ability to absorb energy and resist fracture under the impact of total area under the stress strain curve, while ductility is the ability to plastically deform, stretch and bend without breaking. Tough materials need high strength and ductility. Tough material property defined as the area under the stress curve. Toughness can be determined by integrating the stress strain curve is energy mechanical deformation per unit prior to fracture. Ductile materials include structural steel and many other metals are characterized by their ability to yield normal temperature. For example, low carbon steel generally exhibits a very linear stress strain relationship up to well defined yield point. Importance in engineering. The stress strain curve is a fundamental engineering tool that visually represents a material's mechanical behavior, including its strength, ductility, and elasticity when subjected to external loads. It identifies critical points like the proportional limit, yield strength, and ultimate tensile strength, which are vital for ensuring structural safety and selecting appropriate material for manufacturing. Thank you for listening.